Well, we just had our test on on atomic structure. And so now we're taking this a little bit further. We've looked at a little bit of atomic history. And up to this point, we've talked about how Thomson and Rutherford both had models. And we know that the atom is composed of protons, neutrons, and electrons. So we've found that out. And we also know that those protons and neutrons are in the nucleus. The question is, if you've got these electrons that are negative and the nucleus is positive, you've got those opposite charges, why are those electrons not just diving into that nucleus? Why are they not just pulled straight in? And so Niels Bohr, what he did was he proposed a new model for the atom. And we touched on this at the very end with atomic history. And basically he said that it's the planetary model, that you have these electrons that just orbit the nucleus in these fixed paths. Because of that, that means that those electrons have a fixed amount of energy. And again, it was known as Bohr's planetary model. So that helped to explain why those electrons did not come crashing into that nucleus. Because if you look at how planets revolve around the sun, it's the same type of thing, where you've got, let's see what we've got here, you've got constant motion of those electrons or the planet, and that motion gives that planet the inertia which tends to keep that planet moving in a straight line. Well, you've also got that attraction of the positives and negatives. So in other words, it keeps it in that orbit to where it's not going to come crashing down because of the inertia moving around there. It's also important to remember that, let me move some things here, that Einstein up to this point, Einstein has mentioned, he kind of gave us some ideas about how the mass of an electron, a little bit of that is lost, or mass of particles are lost because it's converted to energy, and so he came up with this equation. But what this really implies is that Einstein is saying the electron must be a particle if we can use this equation with it. So now we're seeing that there's some other ideas that we need to consider. Maybe we also need to think about light and waves. Instead of just particles, we need to think about waves. And understanding the modern view of the atom requires some knowledge about the nature of light. So again, we can think about it as waves moving through space. So if we look at the different parts of a wave, the first thing we have listed here is wavelength. If you were to notice on your diagram, the wavelength is just going to be from any two identical points. The definition here, it says the distance between peaks of the waves or between any two identical points on neighboring waves. So since we're talking about wavelength, we're going to measure that in meters. So it might be from crest to crest, trough to trough, or every other node, because now here's a nodal line, so it might be like this. All right, so that's what we see as far as wavelength. Again, it's going to be measured in meters, just like you would think, because it's a length, so we get that measured in meters. Now, speed, let me go back to wavelength. I didn't even really say anything about this. The only thing that makes this stuff even slightly challenging, really you're going to see we're just using 3-variable equation. But the only thing that makes it just a little bit weird is we start using some funky symbols that you guys might not be familiar with. So this first symbol for wavelength is known as lambda. It looks like kind of a upside down backwards Y, but it's just a Greek letter, lambda. Now for speed, that's our next one that we're looking at. The variable that we use is just a lowercase c. And the speed of light, and for that case, any electromagnetic radiation, and that will make more sense at the end of these notes when I bring that back up again. But the speed of light is going to be 3 times 10 to the 8th meters per second. So just like you would think, you've got some sort of distance over time for speed. And again, it mentions there all electromagnetic radiation travels at the same speed. So that's a part of this that we're going to need to consider as well. Okay, so I just had a question. Should we know the speed of light? Should you know that and have that memorized? And I'm going to go with yes, you should. That's going to be something you use a lot next year in physics as well. So pretty easy. There's not a lot to memorize. There aren't other formulas necessarily that we're going to be working with this unit, but that you should know. Okay, and then the last variable that we'll look at is frequency. And for that, the variable that's used, it's a nu, which isn't really this. There's really a little little leg on that that kind of goes inward. I couldn't find that font very easily. But the Greek letter nu stands for frequency. And frequency is just how often those waves go by in a given amount of time. So the number of waves that go by each second, a complete wave is called a cycle, and the unit of frequency is the number of waves per second, also known as cycles per second. Now the weird thing about this, and I wish I wrote this down. Let's think about that, what that means. If you've got something per second, you would expect it to have those units, right? 1/seconds, and that's the unit for frequency. Another way that you can write that, think back to math, what could you do? It has to do with exponents. What could you write? Seconds to the -1. Good. -1. So those are going to be the units that you see for frequency. I would write that down. And then somewhere in here, I also mentioned that you will sometimes see it written as a hertz. HZ, capital H, lowercase z is the abbreviation that you'll see for that. I typically don't use this so much. I guess I do sometimes, but I'm going to try in my problems. I'm going to try and use these units more often, just because it will help make sense if you're thinking of it in terms of dimensional analysis with these guys. So a hertz is the same as a cycle per second, or just seconds to the -1. So thinking about what that would mean, if you had, well, let's look at our equation first. Here are our three variables that we're looking at, and we can see that how they're related. Remember, c is a constant. So what that means is that does not change. So if your wavelength gets bigger, in order for this value not to change, what does that mean has to happen to frequency? It gets smaller. So in other words, they are inversely proportional is what we end up seeing. So you should just be able to understand what that equation is really telling you. So as one gets bigger, the other gets smaller. Light of long wavelengths have a low frequency, and vice versa is what we end up seeing. Okay, so then if we were to look at an example, here you can see a wavelength here would be from this point to this point. So at one point I said every other node on that nodal line, that's a wavelength. That is the exact same distance as from crest to crest or trough to trough. So that is considered one wavelength. Well, if you have a long wavelength like that compared to this wavelength, then you have, if this is a given amount of time, you can see that you have fewer waves go by when you have long wavelengths. You have more waves go by when you have a shorter wavelength. So that's just illustrating that relationship. Okay, so now we can also relate this to energy. And light has energy. It's the unit for energy is joule. Get used to that because you will see that quite frequently. So energy's unit is joule. It's just an uppercase J that we use. And the energy carried by a beam of light depends on its frequency as well. So that's where this equation comes in. And then we have something known as Planck's constant. Sometimes you hear it pronounced Planck's constant, but Max, oh, here it is, Max Planck. So this constant, 6.626 times 10 to the -3 joules times seconds, is a constant. You do not have to have that memorized. So that would be given to you. You should, I'm going to say that you should know both of your formulas. You should know this one, and you should know this one. So both of those should be learned. But the constant would be given to you. There's no need to memorize that. Okay, so now we've got it to this point where Einstein, remember, he said, yeah, you've got this mass, You can think of an electron as being a particle, having a mass to it. And then Planck comes along and he says, well, actually, we can relate it to frequency, so it must be behaving like a wave. So that's where the debate comes in, and de Broglie comes up with a formula that ties it all together, and it's known as that particle-wave duality. So you can see from de Broglie's formula, which, by the way, that you do not need to memorize. However, with that said, you do need to know some relationships. And the biggest relationship that we need to think about is mentioned down here at the bottom of this page. Basically, it's telling us that anything that has mass has a wavelength. Anything that has a wavelength has a mass. If you look at this formula here, mass is down at the bottom, and let me just kind of go through this formula really quickly. We've got wavelength, we've got Planck's constant, we've got mass down in the bottom, and then this is not frequency, it's velocity. It has to do with the speed of that particle or that wave. So if you have something that has a really large mass, like me, what's my frequency, my wavelength going to be like? The larger the mass, what would you say? The smaller the wavelength. So because this is in the denominator, the larger the mass, the smaller the wavelength. So my wavelength is so small that we really don't notice it very much. But if you have something that has a really small mass, think about what that means when that number's in the denominator. If this number is really tiny, then that means that this number will be bigger. Okay, so that's what that relationship, that you should understand that relationship. That, again, it's mentioned, therefore an electron was both a particle and a wave, known as particle-wave duality. Okay. All right, so now that we're thinking about electrons as behaving as both particles and waves, now we can also look a little bit more closely at light, which is composed of waves, and it has a variety of frequencies and wavelengths. Together, we think of all of these frequencies and wavelengths that make up light and beyond. We think of it all as the electromagnetic spectrum. So those range of frequencies and wavelengths can be divided into bands. We can go ahead, there's a little place for you guys to sketch this on your paper, that we can write down the electromagnetic spectrum and think about some relationships that we see. So I'm going to start over here at the left, and I'm going to write radio and TV waves. In fact, the way I'm going to do this is I'm starting over here with long wavelengths. Okay, and there's a place for you guys to sketch this. All right, so after radio and TV waves, we come to microwaves. Then we get to infrared. Maybe we should write that out. Infrared. Then we get to visible light. And by visible light, what do we mean? The light we can see. So in other words, the colors. You guys have seen this before. Roy G. Biv. Maybe they took out the I when you learned it. Maybe, maybe not. But you've got your red, orange, yellow, green, blue, indigo, violet. After visible light, we've got ultraviolet. We'll write that out. And notice, this makes sense to us. Here is our red. Well, this frequency is less than red, whereas this frequency is greater, ultra, greater than violet. So that's how you can remember those. And then after our ultraviolet, we have X-rays. And then finally, let's just say gamma rays. Okay, so that is our electromagnetic spectrum. Remember that all of these electromagnetic waves travel at the same speed, 3 × 10⁸ meters per second. We know that on our left side, there are very long wavelengths. On our right-hand side, they have short wavelengths. Knowing what we know about the relationship between wavelength and frequency. If we have a long wavelength over here, what can you say about the frequency? What is it? Short, small. So short, or you know what, let me rephrase that. Let me say low. Low frequency. Low frequency, which would mean that there is a high frequency over here. And then, again, if I were to write down, remember this equation that we just talked about? What does that mean the relationship is between energy and frequency? As frequency goes up, energy goes up as well. So if you have a high frequency over here, you also have high energy, which you guys can probably look at that and say, yeah, those have a lot more energy than my radio waves do. So this is a high energy. I'm sorry, I wrote high energy over there. This is a low energy. Okay, so the electromagnetic spectrum and all of that information that we just wrote down, you guys should have a good feel for that and be able to answer some questions about that. Again, you should be able to break it down to those colors as well and remember how those relate to it. Okay, that takes us to some example problems, I believe. And actually, before we do, this is just, again, looking at what we've just already said, relationship of frequency and wavelength. Hopefully you are understanding that they are inversely related. Relationship of wavelength and energy. Again, wavelength, that's going to, frequency and energy are directly related. Wavelength and energy are inversely related. And remember that white light is separated into a continuous spectrum when it passes through a prism. So if you took a prism or a raindrop, something like that, and you shine this white light through it, then you're going to be able to see that continuous band of colors that we just talked about, or what you see right here. And that, let me see if I've got something here. Hold on. Maybe I don't. I thought I put it on your notes. Let me see if I've got it on here. Yeah, I do. I'm just going to jump down to this really quickly. That the atomic emission spectrum, it's on your notes, but I don't have it on the slide here. It's just a set of frequencies of the electromagnetic waves emitted by atoms of the element. So you can see a little blurb above that that tells you about how if electricity is run through a tube that is filled with gas, and then those electrons become excited, in other words, you run energy through it, you're able to actually see it broken down into individual colors. If you look at something like with a diffraction grating, you can see individual lines of color. So in other words, it's not a continuous range of color, and that's known as your atomic emission spectrum. So you guys have that written on your notes. Okay, so now last little thing, this cartoon, I know you can't read it very well. Back in the days when used to read the Sunday paper and have the little cartoons there. It says, do you sell ultraviolet bull? Excuse me? Well, what about regular violet bull? No. Blue bull? No. Green bull? Yellow bull? Orange bull? No, no, no. Well, rats, I'll take a red bull. I was hoping for something with a little higher energy. Get it? Get it? It's the lower energy range. So at least it isn't infrared bull. All right, so here we have a little discussion about a photon. If we're talking about electrons having having properties of both particles and light waves, well, we could also say that a photon is a particle of electromagnetic radiation. It has no mass, but it carries a quantum of energy. So we're talking about a very distinct amount of energy. And so I just wanted to throw this picture in where we can think of light as both the wave and a stream of particles. And the particles that we're referring to when we refer to light particles are called photons. So that's up to you if you want to write that down. Okay, I think that takes us into some calculations now. We've got 3 example problems. And in order to do these, you're going to need to know this handy conversion. So I would write this down somewhere on your paper. And it's just a conversion between a nanometer and a meter. You can write it whichever direction or use it whichever direction you want. Just like it sounds, a nanometer is smaller than a meter. So if you want to look at it this way, one of these big things has this many of the smaller things in it, 1 times 10 to the 9th. Okay, first example. And we've got all the information that we need up above, and of course we have memorized that C equals 3.00 times 10 to the 8th meters per second. And it says, calculate the wavelength of light. So we're looking for wavelength. If we're given a frequency of this, even if it didn't tell you it was frequency, you'd look at that and you'd say seconds to the -1, that's got to be frequency. And we want to calculate this both in nanometers and meters. So first thing I'm going to have to think about is what formula I'm going to use, and hopefully you guys are looking at this one. I am calculating the wavelength. This gets a little trickier. You're going to see that I don't do this so much in dimensional analysis, and the main reason is because of this funky unit. We don't typically work with something that has the unit in the denominator and nothing in the numerator. So if you just change this around algebraically, that might be your best bet in this. So we're trying to solve for wavelength, which means the first thing we need to do is remember that this is wavelength. Lambda is wavelength. So that's going to be equal to my speed of light divided by my frequency. So now, I said I'm not going to do dimensional analysis, but I am going to keep track of my units now as I go through this algebra to make sure that everything cancels out properly. So I know I'm going to take 3 times 10 to the 8th meters per second. I'm going to put that in the denominator. And I'm going to divide that by my frequency, which is 4.8 times 10 to the, I can't read that. What is it? 10 to the 15th. And that's in 1/seconds. So where should I put seconds? Right here. Where should that go? On top, right? Because 1/seconds, here's what we remember. If you if you take something, what we're doing is we're taking meters per second divided by 1/seconds, which is the same thing as saying meters per second times the reciprocal, like that. So that's what we're doing in that case. So now we go through that math, and we're going to get our answer in meters. And we're going to keep it as 3 sig figs. I'm just going to go ahead and write this down. I know they're plugging away in their calculators. Hopefully everybody got that answer. 6.25 times 10 to the -8th meters. And then that last little step, it says, well, do it for both nanometers and meters, so we need to take that value. All it's going to do is change our exponent. So if we want to, I should put a unit in there. If we want to get rid of our meters and go to nanometers, then we know one of these big things, there's 1 times 10 to the 9th of those little things. And so when you go through and do that, you will get 62.5 nanometers. Okay. Questions on that? Move to the last couple. Okay, here we go. Here it says lithium exhibits a red light of wavelength 670.8 nanometers, and when its atoms are excited. And we'll talk more about what that means here shortly, but what we're going to see is that when those atoms get excited, they move to higher energy levels. And it's the process of falling back down to those initial or ground state energy levels that it emits that light. And in the process of emitting that light, it has a wavelength of 670.8 nanometers. So we want to figure out the frequency, and we want to figure out the energy of this light. So we know our wavelength. We know this. We want to figure out frequency because our speed of light is a constant. So here's our formula, and we are solving for frequency. So frequency equals our speed of light divided by our wavelength, 3.0 times 10 to the 8th meters per second. We're dividing that by 670.8 nanometers. Uh-oh, nothing cancels out. We better get our units to cancel out. So I want my meters to be down here and my nanometers to be up here so that those units cancel out. Now you just think about what numbers go where. So I'm going to say one of these big things, one of the meters, there is 1 times 10 to the 9th of these little things. Now I see that my units that I'm going to be left with are 1 over seconds. Yep, that sounds right for frequency. I'm happy with that. So I'm going to let you guys plug that in. Okay, let's see what we got. What'd you guys get on that? Anyone? I have a very sleepy class right now. I'm hearing it. 4.472 times 10 to the 14th is what I heard. Not really. I heard partially. Notice that our answer here should be to 4 sig figs because this is a constant. Because that's a constant, we're not going to use that in our dimensional analysis and trying to figure out our number of sig figs. Instead, we're going to use the 4 right here that are given to us. And then, of course, our units are going to be in 1 over seconds or seconds to the negative 1. Okay, so now what we want to do is we also want to calculate the energy. So we're just going to come in and use a second formula. And we know that energy, here I'll change colors, energy equals Planck's constant times frequency. So it's just going to be, I'm going to change it around and do my frequency first, just because I have it written right in front of me. This over seconds, and then I'm going to multiply that times Planck's constant, which is 6.626 times 10 to the negative 34th, and that's in joules seconds. Which again, that's exactly what I would expect. My seconds cancel out. I'm left with joules on top, which sounds really reasonable for energy. So that's what I would expect. And when we do this, again, we're going to solve it to 4 sig figs. I think we end up getting 2.963 times 10 to the negative 19. If you guys are still having problems with plugging in scientific notation, this is definitely the time to make sure that you solve those problems. All right, we just have one more, and that is number 3. And here it says, yeah. So when I look at number 3, I see the relationship with number 3. It tells me energy, and it's asking for wavelength. Tells me energy, and it's asking for wavelength. Think about what that variable is for wavelength. The only place I see that is right here. I can't do that in one formula, in one step. What do I need to solve for first? I know my energy. I need to solve for frequency. So I'm going to use this equation to solve for frequency. Once I get frequency, I can plug it into this equation and use that one. Okay, so here we go. We're going to say, if we know our energy, we know we're going to use this formula, and we're going to say that frequency equals our energy divided by Planck's constant. So we're going to take our energy of 4.86 times 10 to the negative 20th. That's 20, and that's in joules. I am going to divide that by Planck's constant, 6.626 times 10 to the negative 34th, and that's going to be measured as joules times seconds. So first thing you want to do is just look at your units and make sure that looks reasonable, like you set it up correctly. You'd hate to blow the algebra and have your whole problem be incorrect, and if you think about the units, that'll save you from that. So when you do the math here, you see you get 7.33 times 10 to the 13th. It's frequency, so what do you want to call those units? Seconds. Good. Seconds to the negative 1. Same thing as 1 over seconds. Same thing as hertz, if you happen to see that. If you look on a radio, you see megahertz or kilohertz. for when you dial in the frequency, the radio frequency. Okay, so now we have our frequency. Well, that's going to help us. We can come back to this formula where we have wavelength times our frequency equals the speed of light. Well, we know speed of light. We now know the frequency, so we can easily solve for wavelength. If I can write it, there we go. So our speed of light is a constant at 3 times 10 to the 8th meters per second. I know my frequency, I just solved for that, as 7.33 times 10 to the 13th, 1 over seconds. So remember that flips it back up to the numerator. So now, just like you would expect, our wavelength is going to give us units of meters. You would expect that for a wavelength. And we go through and we see the answer is 4.09 times 10 to the negative 6th meters. If it had asked for it in nanometers, then we would have had to gone another step with the conversion there. All right, I think that is it. So now we kind of see that the electron behaves as both a particle and a light wave, and we can do some calculations with that. Good job.